Hello, welcome to the webinar from Exida. Today we're going to be talking about finding design problems early doing FMEAs with the ARCHx tool from Exida. We'll be talking about the fact that many companies and many engineering managers really know that they can reduce development cost and schedule by finding design problems early in the development process. We're going to talk about how failure modes and effects analysis is well proven and widely used technique used for exactly this purpose. And we'll talk about the ARCHx tool and the fact it was specifically created to provide an intelligent structure for an FMEA, a software HAZOP, and cybersecurity threat analysis. There is a knowledge base in ARCHx that goes significantly beyond failure mode list and HAZOP guide words. And that knowledge base can speed up the analysis and provide more complete, effective evidence for standards compliance. We'll talk about the FMEA concepts and how the ARCHx tool can structure the FMEA by giving you a very high level embedded automation system example. Please note that we will provide copies of all the slides, and we will please type questions anytime you wish, and I will try to monitor the question box on my screen and answer your questions as we go. My name is Bill Goebel. I spent many years in new product development at a DCS safety PLC manufacturer. And as part of that, we got our products certified by what was then called TÜV Product Service. And that's where I learned about functional safety. When there were many things about the whole certification process which we did not like, or I did not like, I was luckily able to get together with Rainer Fowler from Exida, or from TÜV Süd, about 20 years ago. So for the last 20 years, we've been working on functional safety and alarm management and cybersecurity, and we've been able to put together what we believe is a much more effective certification program. Exida is a global company that has basically three separate business groups. There is a group that provides engineering tools, and the ARCHx is part of that tool suite. There is a group that does certification and assessment, and a third group that does system lifecycle services. We do believe that these groups complement each other and help each other succeed. And of course, the relationship between the ARCHx tool and the certification group is a stronger bond because, in fact, it was originally created to help speed along a certification project. I'm very proud that we have strong technical depth. Exida has authored most of the industry references for automation, safety, reliability, and cybersecurity. Many of us enjoy our research work very much, and we study field failure data and we have a lot of very enjoyable meetings discussing and understanding. Just had one this afternoon, field failure data, and compile this information into comprehensive failure rate data guideline books. The certification group started in about 2005 and has become a strong leader in functional safety certification, not only process automation, but machine safety, automotive, and recently we've been getting into a lot of robotics and other pretty fun stuff. We also do a lot of cybersecurity work, and that is the fastest growing portion of our business. Exida manages the Certified Functional Safety Expert personnel certification program. ARC Advisory Group, a market research firm, did a study back in 2015, which kind of surprised us, which shows that Exida was the global leader in functional safety device certifications. And we're very proud of that. And then even the next portion of the study was even more exciting, because even in the logic solver category, and we're talking about safety PLCs, where the very first certifications were done in 1982 by TUV Product Service, Exida has overcome a 20-year head start by our competitors to become the market leader in that segment. But as you can see on the chart, TÜV Rheinland is right behind us. And that means we have to keep working hard. Now, let's talk about the engineering process, because that's the basis of FMEA and the whole concept of the ARCHx tool. Many engineering and quality managers have worked for decades to define engineering procedures and work instructions that will help prevent design mistakes. Maybe I should call them errors. Maybe we should call them errors and omissions, because really that both are very important. Why do engineers do this? For what purpose? Well, when I was an engineering manager, I was rated on meeting my schedule and maintaining our budgets. Now, there's also another dimension to this. We'll talk about it in just a moment, but what is the cost of an error that gets all the way into deployment? Many articles have been written, many studies have been done. Go do an internet search and you will find them. And there's a current one right on the news this month. The Boeing 737 MAX is grounded. How much will this cost? I have read several articles and nobody's speculating much of a number yet, but it looks like it's not good. NASA did a study, which I read, and they said once a product gets into deployment, an error could cost 1,500 times more if it goes to deployment than it would have cost to discover it in the early stages of design. Go read the whole thing if you'd like. I've got a link there for you. The third variable behind maintaining budgets and maintaining schedules is design quality. Both functional safety specifications, IEC 61508, and the cybersecurity specifications, 62443-4-1, have many requirements for the engineering process. And the motivation there is not budgets and schedules, because 61508 doesn't care how much you spend or whether you get done on time. It cares about your design quality. And the process requirements go up as a function of SIL level in 61508 and of security level in 62443-4-1. Both of these standards, in fact, most of our customers want to see high levels of design quality. Now we're going to be talking about how the FMEA fits into this and helps us achieve these goals. And we're going to be using an IEC 61508 compliant development process example from the Exida Functional Safety book. And you want to read the whole book, help yourself. It's available on Exida and Amazon. Any project starts out with specifications. Typically, these are market requirements, customer requirements, use cases, SIL capability levels, SIL certification. I should add cybersecurity certification is more recent. And of course, regulatory requirements, which are present in some countries of the world. once the requirements are finished, we usually start out with a nice, simple, high level, actually, I shouldn't use the word simple, a nice high level design, which we often call an architecture design. Given the requirements, we sit down and figure out how are we going to meet these requirements. Typically, we have a context diagram to establish the bounds of the system, define the interfaces. We end up generating a hardware diagram of some kind and a software diagram of some kind. Or in some companies, they have notation where they combine hardware and software into one drawing. No problem. 61508, 62443 does not care about your specific notation, but it does ask that methods be semi-formal, which basically means unambiguous notation. At least that's how many of us in the certification world interpret those statements, those requirements. What's it going to take for this architecture design? What are the inputs for this particular step? Requirements. What are the outputs of this particular step? Well, typically we have a hardware architecture drawing, a software architecture drawing, additional requirements, updates to the original requirements documents. Many of us call those derived requirements, and perhaps and often required test lists, both integration tests and validation tests. So if we do a good job in this step, we will do a lot to not only create the architecture, create the architecture, but define the testing and document the architecture. And of course, any step has action items, things that must be followed up and tracked till closure to make sure the quality is maintained. For example, imagine our marketing department wants us to build an embedded safety controller. And they say, fine, we want a standalone digital logic safety controller powered by external 24-volt DC power, which is available for both the controller and the I/O devices. It's designed for safety instrumented functions using de-energize to trip conventions. In other words, de-energize is the defined safe state. There are 8 24-volt discrete inputs, digital inputs, that are intended for a contact closure. And we do have a requirement here for stuck-on detection for these inputs. There are 4 24-volt current sourcing digital outputs, discrete outputs, and they must support online pulse-off testing to make sure that many of the components in the output circuitry are still working properly. And there is a specification for 1 amp per channel current sourcing capability. There's a requirement that it's user configurable using limited variability languages and a communications link to provide communications with operator station, engineering station, maintenance station, or peer controllers. Now that peer controllers box down there in the lower right-hand side is important because that does tell us that safety critical variables need to be sent over the communications network. And so we'll have to deal with that in our design. We kind of want to separate these functions into safety critical functions and non-safety functions. And so this is an automatic safety function. We don't depend on any human being to implement the safety function. So we can categorize a set, read the discrete inputs, read remote safety critical variables over the COM ports, over the Ethernet. We need to execute user configured safety functions. And we need to write local discrete outputs to both the output channels on our module and the remote safety critical variables over the Ethernet. Now, those are all considered safety critical functions because they are necessary to implement the automatic protection. There are non-safety functions too. We need to update perhaps an external operating station. We need to respond to external operating system station requests. And of course, we need to send status information to the external maintenance station, especially because we are probably going to be implementing automatic diagnostics. And when there is a diagnostic failure, you must enunciate that to a maintenance station, because diagnostic is of no value unless somebody knows a failure has occurred. Our system designers sit down and go through that. We're going to need some more detail inside that big box. There's a power supply subsystem, and we're going to need some more detail there. And likewise on the input channels, the multiplexer, and the output channels. But that is a good example of a systems level, of the top portion of a systems level architecture drawing. Now, our job, of course, if we want to save money, increase design quality, and stay on budget, is to answer the question, any design mistakes? We'll have to figure out how to do that. Frequently, there is, if there is software, a software architecture drawing is also created at this point, where we can read the local digital inputs, set up a table, use it to execute user-configured safety instrumented functions, read peer variables from the internet, write both local digital outputs to our physical interface, or write safety critical outputs to the peer output table, which will be transmitted to other controllers over the Ethernet communications port. Well, I think that looks pretty simple and straightforward. Do you think there's any design mistakes here? We need to find out. Well, how do you find if there's any design mistakes in an architecture design? The fact is, many techniques have been developed over decades to answer this exact question. This is not new stuff. These techniques include the failure mode and effect analysis, which is, I remember reading, was actually created in the 1960s. Software FMEAs, sometimes called software HAZOPs, which were created more recently, and Cybersecurity Threat Analysis, which is created even more recently yet. I'd say that's less than 10 years old, but I have to go look it up to be sure, so don't quote me on that. After reading about these methods and practicing them, it occurs to many of us here at Exida that these methods are very analogous and use many of the common techniques, which is good because those techniques have been shown to be highly effective. In other words, yeah, it works. The FMEA, I learned about it in the mid-90s. And it was developed over several decades, and it has been a effective and time-saving method. But I have also noticed that there are many, many variations of this. An FMEA, an FMECA, failure mode effect and criticality analysis, and the software FME, and the design FMEA, and the process FMEA, and the threat FMEA. And many of these techniques and many of these names were actually defined by software vendors. And there are many FMEA tools on the market, and many people simply even use a spreadsheet. Why are there all these tools and all these methodologies? Because this method does work. What's the fundamental concept? Well, we have these drawings. What do we do with them? Let's look at the drawing one block at a time. We'll look at the hardware blocks. We'll look at the software blocks. And if you have any FPGA or ASIC functions, which are treated somewhat differently, let's look at those blocks. For every block, we identify what can go wrong. Hardware components can fail. Software can have, they call it defects, or otherwise known as bugs. In other words, it just doesn't do what it's supposed to do all the time. And of course, things can go wrong when we have cybersecurity attacks. Good, we've identified the things that could go wrong. Now, so what do we do now? We identify what can be done to A, verify this cannot happen. And that can be done by analysis or testing. We can design an automatic diagnostic to detect the problem and take appropriate action. Or lastly, we can design a measure to correct the problem when it happens. Good. The basic FMEA procedure, which is typically something we've seen in many of the different FMEA courses, list all the blocks. For each block, list all known failure modes, or create a list of functional failures, typically using a set of guide words, they are called. For every block failure mode, we have to think about what's going to happen. In other words, list the effect of that failure on the next higher level system. In many of these analyses, we have to, or at least we have the option to list the criticality or severity of that effect. And sometimes we'll say, who cares? Seriously, that's just not a problem because of A or B or C. Document that. And the certification assessor will know you looked at it and will either agree or disagree with your justification, but it has been covered. And lastly, list any recommendations or mitigations when these things are necessary. This all seems pretty straightforward to me. This all seems pretty easy. But I can tell you that we've looked at many, many FMEAs in the past. And we've discovered some pretty poor work. What goes wrong? What do people do wrong? Well, they don't have a good list of failure modes. So you might ask, well, where do I find a good list of failure modes anyway? And if you don't have a good list, you're going to miss some of the failure modes. And I have to say that's probably the number one thing that I find. I see people putting together a spreadsheet and trying to do an FMEA, and they don't even list half the failure modes. And what happens if you miss one? You're going to miss a potential errors or omission in the design. You got to have a good list. If you have things that are, yeah, this is pretty bad, we have to do something about it. I need a mitigation technique. Well, are you thinking of the best mitigation techniques? Obviously, the best are things that can be implemented with the least amount of work and are most effective in actually mitigating the potential failure effect. Lastly, as an engineer who does not like documentation, I'm sorry, I just seem to have a problem with it. How do I document all this? Is there a way I can just put this down in a real easy, because you know, I don't like documentation. Let me just find a good shortcut. And some of the shortcuts we find make the work result effectively unreadable. So what we're looking for really is a way to document all this with very little work. fact, I'll be specific. That's what I want to see in a tool. ARCHx is an integrated microcomputer architecture analysis tool. It's designed to support and enhance the problem detection methods used in the design of products for functional safety and cybersecurity. I just give you a heads up, the knowledge bases in this tool are very oriented toward functional safety and cybersecurity, which means we also find lots of problems having to do with correct operation, because that's an essential part of both functional safety and cybersecurity. The ARCHx tool uses a common methodology for hardware, software, and even custom ASICs and FPGAs. It has a tree-based navigation for object nodes for the units, deviations, and measures. And that appears on the left-hand side of a display. And it has object-specific editors for each object type, which appear on the right side of the display. And there's a lot of non-tree based information like project details, reference documents, figures, and action items that can be created and edited on demand. Okay, so what? You have this really cool tool. At least that's what you say. All right, let's take a look at the basic 3 steps. We systematically review all the subsystem blocks. ARCHx calls these units. Why? Actually, in all the different FMEA, software FMEA, and cybersecurity threat analysis, different words were used for the same thing. And so we tried to pick words that could be used across multiple types of analysis so that we could put together a more common method for all these different kinds of analysis. Step number 2, ask what can go wrong. Well, what kind of things can go wrong? We call them deviations, like hardware component failures, software functional failures, and cybersecurity attacks. And then you have to identify what can be done, if anything must be done, and we call those mitigations. So the fundamental objects in ARCHx are units, deviations, and mitigations, and you can see what they are. ARCHx is set up for a structured design system, where at the system architecture, one particular block can be shown as a subsystem. Subsystems can have additional levels of detail, and it can be multi-layers of structure. And this is just a common, ordinary design approach, structured design. In the ARCHx tool, we list all the blocks in a structured way with the unit node editor. And we enter all the blocks all the way down to the level of detail necessary. Normally that's 2 levels, system blocks and subsystem blocks. And the tree diagram is shown on the left side of this display. You'll see all the blocks that we have worked with. And just as a note, the power supply subsystems that we just saw in the last slide are now highlighted by a red box. Point, enter all the blocks, because we're going to look at each one of these. Systematically look at each one of these. You know, just as a side note, some people consider this boring. And it can get a little boring until you find something, and then it gets really exciting. And I've been through many of those too, actually. I've been through a lot of boring and a lot of exciting. For each subsystem, ARCHx knows the type of subsystem and can provide a list of known failure modes from the exida knowledge base. So we've done a whole lot to solve the problem of where do I get a good list of known failure modes. You pick a subsystem, you pick the type of subsystem from a menu, and you will get a list of known failure modes. So that also not only ensures completeness of the analysis, but increases the quality of the analysis and speeds it up. You don't have to argue and sit around and, well, that's not really a failure mode. Yes, it is. Just pick the list. Okay, you don't think something is valid, you can delete it. That's okay, although the certification auditor might challenge that. Now, what I find really cool about it is for each failure mode, the knowledge base in ARCHx provides a list of potential mitigation measures, answering the question, have I picked the best mitigation measure? We've had a lot of experience, and I'll talk about that in a moment. And we have a list of the most effective mitigation measures that our experience knows about. And you can click right on that and pick up those as well. That's pretty good. Now, often there are multiple mitigation measures presented by ARCHx, and then the design team chooses one of them, one or more. Normally it depends on the design and what is to be accomplished and so forth, but the team may very well pick from the list of multiple mitigation measures. If a diagnostic is picked, it's important that the action to be taken on detection of the deviation be specified. Now, for many controllers, especially those oriented toward machine safety, the primary action is to immediately go to the safe state. Turn off the power on the outputs and transmit a trip signal across the network. Now, that's not necessarily, I want to be real clear, that's not necessarily a good thing to do, and especially in process industries. But the key point is, you've got to, right now, think about what action will be taken when a failure is detected. And document it so nobody screws it up. Oh, I have some stories about that you wouldn't believe. People screwing up the action to be taken because it wasn't properly documented anywhere. But we don't have time for all those stories. Often when you're going through a set of failure modes and mitigation levels, you may discover that there's something that must be investigated before we can mark it checked off and completed. And an action item tracker is used to make sure that we trace these problems to resolution. If you need an action item, just hit the Add Action Item button, and up pops an action item editor where you can put in what you need to do. For example, we need to verify what's the minimum operating voltage of all the safety critical ICs using this 3.3 volt supply and set the low voltage trip threshold above this level. We don't know what it is, but somebody's got to check all this and make sure this happens. So that's what action item trackers are all about. Of course, we have to generate documentation. So ARCHx allows you to enter lots of project details, names, numbers, project leaders, staff, creation dates, version numbers, companies' names and addresses, target SIL levels, target security levels, if that's applicable, and a bunch of additional reference material, including figures and reference documents as required. That's just part of good documentation, and it's better to type them in right now than to type them over and over again in different reports. That makes me happy, one who does not like documentation. All right, I talked about this knowledge base. What is it? It's a collection of deviations, failure modes, functional failure modes, and mitigation suggestions for both safety and cybersecurity. That is, and this is the fun part, that's both context and content specific. It knows where you are. The tool knows where you are in the process and what type of functional architecture building block you're working with, and will provide knowledge, failure modes, deviations, and mitigation suggestions as a function of the context. The ARCHx knowledge uses smart renaming that automatically edits suggested content to maintain consistencies of words and vocabulary. The expert knowledge base is really a pretty nice advancement over the conventional HAZOP guide words, because there are specific deviations depending on the exact type of subsystem building block that's being used. Of course, the generic HAZOP words are still there if you want them, or you can hit the button and they will be entered into your program, so you can go through those to see if there's anything you've missed in your design. All right. I know when I heard about this, I wanted to know, how does exida get this knowledge? Because there are many top experts in the field who have long-term experience on previous projects. For example, a top expert at an OEM development company may have knowledge based on multiple products or perhaps 30 years of experience. Now, I worked over 25 years in a DCS safety PLC company. And I will tell you that in that time period, we had 2 generations, 2 projects. Doesn't seem like much over 25 plus years, but you invest that much money in development, you got to sell it for some time, sell it and maintain it for some period of time. And that's good experience, and I really liked it, but it's different when you're a certification company. Exida consultants are specialists involving 5 or 10 diverse projects per year, with our consultants having 10 plus years of experience, plus 10 to, and of course, many of our people have 10 to 20 years of prior experience before joining exida. So we have maybe 3 to 10 times the experience of top experts in a development company, with more weighting in recent years, which is really important for the dynamic change created by our technology. Now, I got a question. If additional deviations and mitigations are identified later in the design, via an improved knowledge base, does ARCHx have a feature that will assist with design review with this new knowledge? I have to admit that I specifically do not know the question, the answer to that question. I do know that the knowledge base is updated typically 2 times a year. And I will tell you that right now, most of the dynamic change in the world is in integrated circuits, and all the things we're discovering about the small geometry integrated circuits. We're also adding blocks, but I don't really know if there's any special feature that will assist with a design review which specifically highlights all the new changes that may be relevant to a project. But if it's okay with you, I will make sure we put that on a target list of things to be reviewed for future enhancements to ARCHx. Now let me give you another example of the knowledge base. In this example, the design has internal SRAM. Okay. Now to get a list of the failure modes for internal SRAM, we highlight the internal SRAM and click on it. And there's a list of all the different types of blocks. And we're going to pick hardware RAM and click on that. Then we go to the deviation library and verify that we want the hardware RAM box. And we hit the load subtree button and pop. Up comes the mitigation measures. So we have now a list of failure modes for the internal RAM and a list of suggested potential mitigation measures. 1, 2, 3, 5 for hard faults and 4 for soft single event upset faults. Now those are kind of a big deal. We're going to talk about that a bit more because it's kind of new. And let's assume that the microcontroller for our example has built-in ECC for guaranteed correction of single faults and detection of double faults and detection of many other multiple bit faults. So we're going to click on the mitigation measures not used and press delete for the checksum, for the parity, for the CRC verification, leaving only the last one marked M87, ECC of internal SRAM SEUs. Now go to the remaining measures and read the notes, and let's check the notes for that. Now, here it is. Let's click on that and just see what this is all about. Boy, there's some good notes, some good information here. The level of effectiveness and diagnostic coverage is highly dependent on, This issue can substantially affect operational failure rates of any device. We have learned that embedded microcontrollers used in critical functions must behave very differently from the embedded microcontrollers used in a cell phone. I don't keep good records, but I know for a fact that, well, no, I should say I don't keep good records, but my feeling is that my cell phone seems to fail about twice a week. No, it's just my guess. If I had a safety critical embedded microcontroller that failed that much, it would be a disaster. So the choice of the microcomputer integrated circuit is a major design decision. It's done during architecture design, and we need to understand the implications of our choices. This issue will, in fact, though, most likely require additional research, because the semiconductor manufacturers may not make the numbers we're looking for very obvious. But we must get additional information to properly complete percentages of failure distributions and diagnostic coverage, which we will need later on in the design process for a task called FMEA. So typically we will use the action item editor to record the need for this important additional investigation. And we'll go ahead and type up an action item that we need more detailed information on the SRAM to determine diagnostic coverage. Clock it in. Good. Now, what happens when we're all done reviewing all these blocks, all these units? We have a list of problems and issues, which ARCHx calls deviations. For each deviation, we add a prevention measure requirement or a diagnostic measure requirement or define tests to show that this theoretical issue is not plausible. These are things we call mitigations. And often, design changes are made to enhance the design, and therefore derived safety requirements are created. I see another question. Thank you. How does this tool interface with the FMEA tool? Let me increase my screen size so I can do a better job reading the rest of that. How do we share the work done here? Okay. The bottom line is that ARCHx provides automatic report generation. There are many predefined reports available in ARCHx, and all the information captured in the analysis can be extracted using the automatic ARCHx reports. There are mitigation measures to provide input for use by the development team and your functional safety and cybersecurity auditors. There is a prevention mitigation measure list that tells us what we need to check for in our processes and our procedures. There are derived requirements reports, which tell us what we need to add to our requirements documents. And there are needed integration and validation test reports that tell us exactly what we need to add to our integration test planning and our validation test planning. All the deviation and mitigation measures can be exported directly to the exida FMEA X tool, which saves a lot of time and effort rather than re-entering them, and it eliminates transcription errors. The information then has you all set up to do an FMEA X, showing, in other words, showing all the functional failure modes, the failure mode distributions, and the diagnostic coverage effectiveness of any diagnostics actually chosen for the project. Now, if new or custom reports are needed, they can be developed and added quickly as new needs are identified, because the report generator is independent, data-driven, and doesn't need a tool version update, which is kind of cool because there's lots of new stuff going on in the world every year. So let me just summarize. A lot of us in the engineering world have worked hard to create procedures to reduce design errors because I was always rated on my scheduling and my cost. And when I got a project certified for functional safety, I was rated on my design quality when I was an engineering manager. The procedures created by most companies include error checking in each step of the process. But as I said earlier, some of this error checking work is really not very good. And often the company doesn't know that. It's a checkbox. Did you do the FMEA or not? Well, there is a lot more necessary in terms of quality. Tools help enforce quality. An FMEA, a software FMEA, a cybersecurity threat analysis are well-proven techniques for finding design errors and omissions, and tools like ARCHx decrease the chance for an error. I'm not saying that's the only tool on the market. Actually, there are many. And I'd rather have you do an FMEA with a spreadsheet than not do one. It's just you have some potential problems which are eliminated by many tools. If you'd like to know more, we have two additional webinars, more about ARCHx in particular. We have 2 additional webinars coming up in the next 2 weeks. Today, we talked about FMEA using ARCHx. Next Wednesday, we will talk about cybersecurity threat analysis using ARCHx. And on Wednesday, June 19th, we will have a specific webinar on software FMEA using ARCHx. So we'll show you how these 3 techniques are used with one common tool. If you need any more information, please look at the exida.com website. We have many recorded webinars and white papers. If you have any questions, go right ahead and try and type them in now. If you have a question that pops into your mind later, please don't hesitate to send me an email. My email address is one word in the beginning, wgoble@exida.com. And you can also check for the latest information on Twitter, Facebook, or LinkedIn. I don't see any other questions. I do want to thank those who have typed in some good questions. And hopefully you found your time well spent. Think about the next round of webinars for Exida, and especially for ARCHx. And we do have webinars on FMEA, the companion tool. Just checking again for any more questions. I think we're fine. Thank you all for attending, and hopefully we'll see you again soon. Goodbye.